This is Bernard Paulson. We have come to the very last lecture associated with this book. In this final and last chapter, we talk about how to describe a regulatory enzyme and how it is integrated with the pathway that it regulates. Regulatory enzymes were discussed in chapter 5, and these are extremely important enzymes in metabolism as they sense the level of a number of metabolites and adjust their catalytic activity accordingly. So the outline is as follows. We are going to be focused on phosphofructokinase, or PFK, in this lecture. Historically, this enzyme was seen as the key regulatory enzyme in glycolysis, and in some textbook is referred to as the pacemaker of glycolysis. Of course, glycolysis has other two notable kinases, hexokinase and phosphofructokinase, that are very significant regulatory enzymes as well. We will look at a simplified version of PFK in this lecture. It is a very complicated molecule and can bind to many ligands. We will describe two of them. And we will describe the bound states of the enzyme with activator molecules and with inhibitors. And based on that, as before, we will formulate pools of concentrations of certain properties and ratio some of these pools to describe functional states in bioengineering terms. We will then integrate with glycolysis and talk a little bit about the constraints that are put on that subnetwork as it goes into the larger network. Turns out that the activity of regulatory enzymes, the selection of their kinetic constants and so forth, is fairly constrained given the environment that they work in. So phosphofructokinase 1 is the enzyme we will be talking about in this lecture. Here is the pathway map that we looked at earlier. And the second phosphorylation step in glycolysis, where where fructose 6-phosphate is converted to fructose 1,6-phosphate. And that reaction is carried out by PFK that we will study in here. So in our skeleton mass action model of glycolysis, this conversion is a simple bilinear reaction where the two reactants react with a perk to be converted into the product. We are now going to take this simple arrow that is shown there and detail its underlying mechanism. So a little bit of background to give us some biological context here. So as with many regulatory enzymes, PFK is a tetramer. It has 3 isoforms: muscle, liver, and platelet forms. What this means is that there are 3 versions of the gene on the genome of slightly different sequence and properties, and these genes are expressed differently in different tissues. So the muscle form of PFK is, for instance, expressed in muscle. The tissue distribution of the expression of isoforms is of great interest, and there is much attention being devoted to determining such expression patterns currently. As we saw in chapter 5, regulatory enzymes often naturally exist in 2 conformational states, even in the absence of any ligands that could bind to the enzyme. And these are referred to as the relaxed state and the tight state, sometimes called also the taut state. So in the relaxed state, the catalytic site is open and the enzyme can carry out its catalysis. In the tight state, the active site is closed and the enzyme is inhibited. The allosteric constant, L for PFK, is given in the slide, and this is basically the equilibrium constant between these two natural conformational states of the protein. Now, there are a number of inhibitors and activators that can bind to this enzyme, as with other regulatory enzymes. And we're going to treat two of them here. We're going to treat ATP as an inhibitor. So as ATP concentration builds up, glycolysis would slow down because there would be enough ATP around. Conversely, an AMP is an activator. And as we've seen, AMP levels are very sensitive to any perturbation in the ATP load. And so this molecule can be used as a sensor of the need for ATP generation. The reaction that PFK catalyzes is very simple and is shown at the bottom, where ATP binds to fructose 6-phosphate to form the fructose diphosphate and release ATP and a proton. Why do we want to model PFK? Well, we already mentioned the fact that it is one of the most important regulatory enzymes of glycolysis. So including it in a simulator would make the simulation more realistic. As we saw in lecture 12, there are often genetic defects associated with enzymes, and PFK is no exception. Recently, there has been renewed interest in the rates of glycolysis as high glycolytic rates are observed in tumors. This is known as the Warburg effect, after Otto Warburg, who got the Nobel Prize in the 1930s for discovering that tumors tend to grow anaerobically with a high glycolytic rate. And finally, and this is kind of a mantra of the module by module construction that we're going through here, is this quote by Richard Feynman, the famous Caltech physicist, where he says, "What I cannot create, I cannot understand." So we are trying to build module by module, brick by brick, part by part, large-scale simulators of biological phenomena. And as we build them to increasing complexity, it's easy for us to understand the origin of many effects as we see them being laid down into the simulators that we are building. Now, here is a somewhat complicated diagram that describes the PFK module that we're going to build. On top, we have the regulatory events. So if we start out in the top left-hand corner of this dashed box, we see T0, which is the taut state without anything bound to it. It's in natural equilibrium with R0. T0 can bind to 1, 2, 3, and 4 inhibitors, pulling it horizontally across this diagram. And the same thing with R. It can bind to 1, 2, 3, 4 activator molecules that pulls it more and more into the R form. The concentrations of the inhibitor and activator are simply those concentrations in the metabolic network. And for AMP and ATP, we do know these steady-state concentrations from the mass action stoichiometric simulator, and those are, of course, the concentrations we can use in building this module and its steady state. The lower half of this dashed box is the catalysis itself. Here we see substrates flow in, the ATP and the fructose 6-phosphate. They bind serially to one of the R forms, loaded up to the AF form that is shown at the bottom. That is the version of the enzyme where both substrates are bound, and then they bounce off of one another, carrying out the catalytic reaction. Products are released, and the free enzyme is liberated. Notice that the R0, R1, 2, 3, and 4 forms all carry out identically the same reaction. In a way, this is like a multiplexer with 5 channels, and the flow will go through each one of these channels just depending on the relative abundance of R0 to R1 to R2, 3, and 4. The state of the system is a tug of war between the T and the R forms, as we shall see. To build the steady state module, as I mentioned, we have the concentrations of the regulators, which will be in equilibrium with their binding sites. But the substrates and products, on the other hand, flow in and out of this module, and we know the steady state flux through PFK from the mass action stoichiometric model, and we can fix those numbers, and we also know the concentration of ATP and F6P, and all this information, as we'll see, is going to be used to determine the kinetic constants we need. So the catalytic mechanism is first binding of ATP to any one of the forms. Here I can be 0, 1, 2, 3, or 4. Binding of the second substrate. Then the reaction itself, that actually should be irreversible with a unidirectional arrow that liberates the products. And put this image in here to remind you of the things we spoke of in lecture 2, namely that the enzyme puts the substrates into the right proximity so that they bounce off of one another optimally to have the reaction take place. Now, the ligand binding steps are simple. Here are the 4 steps, serial steps of the binding of an activator, the natural equilibrium between the 2 conformational states of the free protein, and then the serial binding of the inhibitor. As before, we can now build a stoichiometric matrix for this, and it is quite complicated given the number of reactions that are accounted for. We have the inputs and the outputs that we are going to fuse later with the glycolytic model. Then we have all the activation and catalysis steps. These are actually 5 blocks of similar reactions because each channel, so to speak, that goes through the enzyme is the same. Then we have the serial binding of the inhibitor. And there are 5 pathways through the system, which are just being the inputs of the products, of the reactants, and outputs are the products. And as you see in the band diagonal structure of that box at the bottom in dashed, there are 5 identical throughputs through the enzyme shown there, 1 for each pathway, that illustrate the 5 parallel paths that can go through this enzyme module. Now, how do we characterize the enzyme? Well, there are the R and T states, and there's the summation of all forms. The relative amount of these is very important. We define 2 ratios here that we find to be useful. One is the amount of the enzyme that's in the R form, and that's that R sub R. So that will be the fraction of the enzyme that's in the R form. And then there is the R cat, which is the fraction of the R forms that's in the catalytic state that carries out the reaction. That's Ri, AF, which corresponds to the intermediate state that we studied so extensively in chapter 5. For the numerical values that we shall use and talk about here in a moment, the RR is 90%, which means that only 10% of the enzyme is in the inhibited form. Most of it is in the active form. And out of the enzyme that's in the active form, about 12% of it is bound to both of the substrates and is busy carrying out the reaction. So that's how we characterize that steady state. I should comment right away on the fact that since RR is 90%, the enzyme and its catalytic potential is heavily utilized, since only 10% is in the T form. But that also means the ability to activate this enzyme is limited because the enzyme is already 90% in the active form, and you can only deploy 10% more enzyme out of the T forms under a perturbation condition. Okay, now we're going to determine the steady state. I want to revisit the subnetwork with a little more pictorial representation. The T forms shown on top are indicated by a square. This is what we used in chapter 5. And as we go up top, you see more and more of the squares being shaded, meaning that that binding site is occupied by an inhibitor, ending up with T4, where all the binding sites are occupied. The two circles below in the closed box indicate that the two binding sites are closed off in the T form. The R form is indicated by a circle, as we did again in chapter 5. If you go horizontally across, you see the activator load onto the R form until all 4 slots are occupied in R4. Then there are 5 catalytic cycles shown, each one carried out by the different R forms. And you see below that R circle, I have now opened up the binding sites. They're exposed on the enzyme, and they can bind first to ATP. So one of the binding sites is gray. Then it binds to F6P, so both the binding sites are gray now because both the substrates are on the enzyme, and then the reaction happens, the product is released, and the binding sites are open, again, ready for another round of catalysis. So, in the steady state, a number of reactions here are at equilibrium, so that means that T and R are in equilibrium, and so are the binding states of the activators and the inhibitors. Because these represent dead-end reactions. There is no net flow through these forms. Conversely, the reactions where there is net flow through are in a steady state, and the steady state flux is the flux level that I spoke of earlier, which comes from the stoichiometric scaffold model. We know what the flux through these 5 enzyme catalytic states are in the steady state. All these 5, the fluxes through all these 5 have to sum up to being the steady state flux through the pathway. Conversely, the binding states are determined by equilibrium relationships of the ligands. So that's the picture. Here's the mathematics. It's very complicated or looks complicated. We have the activation steps. We have the inhibition and conformational change steps, and then we have the catalytic steps. Note that these reactions are written out where the enzyme is in a fixed environment. This means that the ATP concentration is fixed, the F6P concentration is fixed, the binding of the activator and inhibitor is fixed, and therefore these are all linear kinetic equations. They all are a rate constant times the concentration of one form of the enzyme. The concentration of the substrates and so forth is built into these kinetic constants. These concentrations are fixed because they determine the metabolic environment that this enzyme module is going to be integrated into. This introduces a number of constraints on the system. As I mentioned, we can measure the total amount of enzyme, and all the forms have to sum up to that total. The total flux will be the turnover rate times all the intermediate states that have both the substrates on it. And at the bottom, there are the equilibrium constants of binding, and these will be known. Turns out that these algebraic equations can be solved symbolically using Mathematica, and here are all the relative forms of the T and R forms for this module. And all we got to do is to plug in the numerical values here to figure out what is what. The equilibrium constants are known, so for the forward rate constants in the equilibrium reactions disappear in here when you do the algebra. And this leads us to one equation with three unknowns. These are the on rates for ATP, for fructose 6-phosphate, and then the turnover time. And these three are related to one another, and this is a hyperbolic type surface as shown over here, and only values for these kinetic constants on this surface will satisfy all the constraints associated with the network environment that we're going to put this enzyme module into. We have chosen this point as the steady state for reasons described in the text. You could pick any one of those that you like.